So this video is meant to work through some exponential growth and decay problems as it relates to differential functions or differential equations in calculus. What you see at the bottom of the screen here, where it says dy over dt is equal to ky, that is our differential equation. On the left side of the equal sign, we have the derivative of y with respect to the derivative of t, the derivative of y with respect to t. So t would be considered our independent variable, whatever it is, typically time, and y is going to represent any number of outcomes, whether it is a population, money, or some other thing that we happen to be talking about in context of a problem. Now, growth and decay functions should not be a new concept to a calculus student because in Algebra 1, you typically will get introduced to simple exponential functions. As you go through Algebra 2, pre-cal, you're going to see more applications of growth and decay functions where we're modeling population rise and fall with exponential functions. You can do financial applications with continuously compounding functions. And even from chemistry, you may have seen half-life equations where we have the exponential equations that we're going to be working with, meaning that we have some kind of a base and the variable that we're working with is in the exponents position of your problem. So now what we're going to do is we're going to work our way. Let's get through some of the math kind of technical stuff that we have to talk about here. So the differential equation that we started with, dy over dt is equal to k times y. Well, k is going to represent some constant of proportionality in the exponential function. Now c is typically going to be an initial amount of some kind, and y could be an output of whatever we want it to be. So y might be considered maybe p of t for if we're talking about population. Maybe it could be a of t if we just are generally referring to amount of some, some topic, some like number of atoms for a decay function for half-life. But y is just going to be the output, and a lot of times you'll see it put in context where we kind of have our whatever the first initial is over to where time is your exponential or is your independent variable. Now down at the bottom, it's going to show you that we have, if k is going to be greater than 0, we have an exponential growth, and there is a typo here in the second part. It should say when k is less than 0, that's going to give you a decay model. So what we want to do first is we want to see, well, how does that differential equation, dy over dt, to be equal to k times y, become this function here that is going to be a very standardized type of function when it comes to growth or decay models or functions. Well, we have the differential equation dy over dt is equal to k times y. And this is a separable differential equation, meaning we can isolate the variables of the equation on one side. So I'm going to begin by multiplying both sides by y to remove it from, or by 1 over y to remove it from the right side of the equation. So I'm going to get 1 over y times dy to be equal to, and multiply both sides times dt, and I'm going to get k times dt. So we've separated our variables by getting y on one side and t on the other side. And now, at this point in the separable differential equations that we have, this is where our calculus really comes to point. We're going to integrate both sides. So on the left side, the antiderivative of 1 over y will be 1 multiplied by the natural log of y, and it will be equal to, now k is just a constant. We could pull the constant k out, and we could write it as k times the integration of dt if that makes it a little simpler. But when we take the derivative, the antiderivative of dt, that's going to give us a t that gets multiplied to the constant k. And because this is not a definite integral, we have an indefinite integral that we're working with here, we do need to add our constant. So I have the natural log of y to be equal to uh, t times k plus some constant c. Now, this c that I've come up with so far in the problem is not that capital C that you have in your standardized equation on the right of the screen. There, remember in our differential equations, when we take the antiderivative of something, uh, the c is just going to be a constant. It is a family of solutions and can be a whole bunch of different numbers. Well, at this point now, essentially we want to try to isolate y. We want to get that y by itself. So from here, what I'm going to do is I'm going to use some properties of logarithms, and the base of the natural log is e. So using a log loop, I'm going to say e to the tk, and that is a terrible k. Let me see if I can fix it a little bit. T times k plus c power will be equal to y. Now, we've got y by itself, but on the left side of the equation, we definitely need to clean it up a little bit. Well, using properties of exponents, we're adding the exponent values together, so I can rewrite the left side of the equation as e to the t times k power times e to the c power is equal to y. Well, this guy right here, this is just a constant, because E is going to be whatever E is, 2.718, but C is still going to say that that value there, whatever it happens to be, is going to be just a constant. So I write that as C, and that's where that big C in our standard equation comes from. So the left side of the equation now becomes C times E to the tk power, or let's go ahead and reverse that because that's how the equation is generally written, is it generally says k times t, and I can't write a k very well for some reason today. So k times t power is equal to y. Or if you need to see it the other way around, y is equal to c times e to the kt power. And that is where the standard equation comes from our simple differential equation. Now, taking a look at, so that example was just to show you where, just to prove where the equation came from, where the growth model comes from. Now we're going to be looking at it in terms of some context, and we're going to be applying it to some problems. So here in this example, the rate of change of y is proportional to y, and that's good because we need that for our exponential growth. When t is equal to 0 and y is equal to 3, and when t is equal to 2, y is going to be equal to 6. So what is the value of y when time is equal to 3? Okay, now the time can be kind of anything. It doesn't necessarily have to be uh, years, it could be months, it could be days. It's just going to be some value of time. Now, starting off with, we have that general equation that we just solved for, where we said y is equal to c times e to the kt power. That's our general equation. Well, we have some values of t that we could use in the equation, and we even have some values of y that we could use in our equation. The one thing that we absolutely don't have is we don't know the value of c. We don't know what we can use for c, or we don't know what k is going to be. So those are going to be two things that we're going to have to find. Now, the first thing I'm going to do is we're going to find, let's find the value of c. Okay, well, we're going to take this initial condition here. When time is 0, the output is going to be 3. So uh, we can use that very easily to find the value of c simply because t is in the exponent position. You'll see what I'm talking about here in just a second. So we have the equation. Let's go ahead and substitute 3 for the y to be equal to c times e. Now k, we don't know what k is either, but we'll go ahead and put k there. Now time in this case is 0, so we substitute 0. And what you're going to see very easily is that k times 0, it doesn't matter what k is, that is just going to give you e to the 0 power. And anything to the 0 power is 1, so c is 3. Now what I want to do, and I'll pick another color here for this. Now that I do have a value for c, let's say that this is our second thing that we're doing. Let's find k because I need my equation in order to be able to solve the question that it's asking. What's the output when t is 3? So let's find k now with our given conditions. So we're going to look at using these values here for finding k because we don't want to use 0 because k times 0, we don't want to use the stuff that I did in red because that'll give me k times 0 again, which will make 0. So we definitely want to use the second points that they gave me to find the value of k. So we start off by taking our y value, which in this case will be 6, to be equal to, and now we know a value of c, that's going to be 3 times e to the k, and in this case, time is given to you to be 2, so we have that. Now we're going to just solve this equation in terms of k. We need to get k by itself. So begin by dividing both sides by 3, because 3 is multiplied to e. And so that'll give you 2 is equal to e to the 2k power. Let's just kind of write that in a more standard notation. And at this point, the only way that we can get k out of the exponent spot is to convert the exponent into a logarithm. So again, properties of logarithms, we'll use a log loop here. So I will take the natural log of 2 will be equal to 2 times k. So that means the natural log of 2 will be divided by 2 to be equal to k. Now that is not necessarily going to be a very nice number. You can take that number and type it into your calculator and simplify and save the number if you want to. Now let's simplify this just a tad. We're going to say I can write this as 1/2 times the natural log of 2, which again, properties of exponents, the number in front of the logarithm can be written as an exponent of the number that you're taking the logarithm of. So that would be the natural log of 2 to the 1/2 power, or the natural log square root of 2. Okay, and that will be, this will be the version of k that I'm going to finish the problem with. So now we want to be able to find the value of y when time is 3. So what we've done so far is we've established the initial uh, conditions of at time 0, c is going to be 3. We have our constant of proportionality, k, to be the natural log of the square root of 2. And that will give us our equation to be y is equal to 3 times e to the k power, which in this case will be the natural log of the square root of 2 times time. And now it simply becomes a plug and chug exercise on your calculator where you plug in 3 for time. So we get y to be equal to 3 times e to the natural log of square root of 2 times 3. And when you type that into your calculator, you're going to get y to be equal to, well, not equal to, let's do this properly, because it's not going to be a nice number. It'll be approximately equal to 8.5 485. And that's the end of that example. We do have to do a little bit of work. Hopefully the explanation is helping some. Now for this example, if you feel at all confident about it, go ahead and try working the problem out in advance if you feel comfortable trying to do so. And just pause the video and work it out. And when you're done, hit play and see how I did everything. So here, the number of bacteria in a culture is growing at a rate of 3,000 times e to the 2t over 5 power per unit of time. Time is equal to 0. The number of bacteria present was 7,500. So find the number present at time is 5. Now we don't know what time is. It could be minutes, days, months. We don't know. But this right here at time 0 and 7,500, those are your initial conditions. That is your initial condition. So what I'm going to do is I'm going to say, well, we have, instead of saying y is equal to, I'm going to put y to be equal to b of t, where I'm going to say bacteria over some amount of time. So our generic equation, our standard equation that we're working with for growth and decay, I'm going to say b of t 2, b of t will be equal to c times e to the kt power once again. Okay. Now we know that the initial conditions were 7,500. That is C. At time 0, that's what you start with. We know that we're looking for time at 5, and really that's all we need in order to be able to answer this question. We're just looking for the number of bacteria, so this will be a simple plug and chug exercise. So I'm going to say B of 5 will be equal to 7,500 times E to the, and we know the K power that was given to us, so that will be 2/5, that's K, and T is 5, so the 5's simplify to be 1. So 7,500 times E squared will give you B of 5 to be approximately equal to 55,417.921 bacteria. Now again, moving on to the next example, feel free to pause the video and try to work the problem out on your own in advance, and then go back and see how I'm going to work it out. But presuming that you've done that, now we're going to be taking a look at economy. We're going to be talking about money, which is really useful. Be prepared to be surprised with some things that you will learn in an economics class in college if you haven't already taken it in high school. There's definitely going to be some things that are going to open your eyes, I hope. And when you really take an economics class dealing with, how the money actually, works, there's a very good reason why we need to have some high-level math skills. So a slow economy caused a company's annual revenues to drop from $530,000 in 2008 to $386,000 in 2010. If the revenue is following an exponential pattern of decline, what is the expected revenue in 2013? So in this case, I'm going to take our equation that says y is equal to c times e to the RT kt power, not RT. And I'm going to make y, I'm going to call that R for revenue. So I'm going to say R of t is equal to c times e to the kt power. So what do we know? We know that in this case, we started in 2008 and in 2010, so we definitely have a change of 2 years. So in time, was 2. When 2 years passed, that gave us a C value of 386. Well, let's back this up. I'm not starting at the beginning, and that's bad, Mr. Piercy. So we know that at time 0, our initial conditions, so at time 0, when no years have passed, C, the amount present for revenue, was $530,000. Well, 2 years later, the revenue had dropped to $386,000. Now, in order to be able to establish what it will be in 2013, 5 years after you initially start losing money, we definitely need to be able to find the value of K. That's really the only thing that's missing. So let's find K first, and we'll pick another color here for K. So let's find K. Well, we know that at some point in 2010, they had a revenue of $386,000. And the initial amount that they started with at time 0 was $530,000 times e to the kt power. Now, in this case, for the time to get to the $386,000, time has to be 2. Well, we can solve this equation. We have enough information now that we can solve this for k. So begin by dividing 386,000 divided by 530,000. And I don't know what that is as a decimal number. It's not a pretty decimal number. So as a fraction, it simplifies to be 193 divided by 265. And that will be equal to e to the 2k power. And as you've seen a couple times in this video already, to get k out of the exponent spot, we will do a log loop, properties of logarithms. So that will give me the natural log of 193 over 265 to be equal to 2 times k. And so you divide both sides by 2, and that is going to, when you divide that by 2, that's going to give you about 0.159 to be approximately equal to k. Now, this number here that we have for k, make sure you save this number in your calculator, because we don't want to do any math with a rounded number. So save that number in your calculator. Otherwise, make sure that you write down what k actually is as an exact number, natural log of 193 over 265, and the whole thing divided by 2. Okay, so now that we have k, now we can find out what the projected revenue will be in 5 years in 2013. So next we can actually solve the problem that we were given. Find R of 5, which would be the year 2013 when 5 years have passed since the 2008 initial time. So this is going to give us R of 5 to be equal to the initial amount, $530,000 times E to the and this is a negative number. I forgot to put the negative sign on the K value. It's definitely a negative number because we are experiencing a decline. Hopefully you guys weren't screaming at your monitors too loudly. So we have negative 0.159. Now remember, I'm rounding it here, but on your calculator you have that number saved. And so when you type that into your calculator, that will give you your revenue after 5 years to be approximately 239,000. Oops, $239,913.37. So I hope you guys are starting to see a pattern emerge with these types of problems. They're always going to give you obviously enough information to get started. Sometimes you're going to have to solve for K, sometimes you're going to have to solve for time, sometimes you're going to have to figure out what the initial amount was for C first, um, and then you'll be able to probably actually answer the question that they're giving you. Okay. Now, as far as complicated problems go, this example here is probably one of the more challenging ones to kind of think your way through. But again, don't let that scare you off from trying to work it out on your own. So please feel free to pause the video and try and work it out ahead of me. And when you're ready, go ahead and hit play. But presuming you've worked your way through the problem, let's take a look at it now. Suppose a population of insects increases according to the law of exponential growth, so we know we're in the right wheelhouse. There were 130 seconds, or 130 insects, not seconds, after the third day of the experiment, and 380 insects after the seventh day. So we know we're dealing with T is going to be days. Approximately how many insects were in the initial population? So how many insects were in the initial population? That's telling you to find C. We want to know the initial amount that you had at time 0. Well, we don't know what that is right now, okay? But we do know that at time 3, at 3 days, we had 130 insects, and at 7 days, we had, excuse me, 380 insects. Well, here, these two bits of data that they're giving you, even though the initial conditions aren't given to you, the initial conditions can be found with this information. So let's see how we're going to do this. Now we know we have our equation of y is equal to c times e to the kt power. That equation isn't going to change. But we do know that at some point, time is going to give us 130 insects. So I have 130 insects is equal to c times e to the, and we don't know what k is right now, so we'll just say time is 3, so 3k. And we also know that we're going to have 380 insects when we have c times e to the 7k power. So how are we going to use this? Well, I'm going to take these two terms, let me pick another color here. I'm going to take these two things. All we're doing is we're taking the information from the problem and substituting it directly into the equation. We have two generic equations that we're working with. Here, this is going to give me enough leeway to solve for C, then to solve for K. So let's see how we're going to do this. Now, if I take the first equation, let's move down here so I have a little bit of room. I'm going to take this first thing that I have written. 130 is equal to C times blah, blah, blah. I'm going to divide by the E term to get C by itself. So that's going to give me 130 divided by E to the 3k power. And that is going to be equal to C. Well, now that I don't actually know what C is, but now I have an expression that I can substitute here to find C. And let's do that in another color. So let's go red here. So I'm going to take this expression and I'm going to substitute it into the second equation that also contains C. Now remember, C is going to be the same. It's the initial amount present when you begin your process of whatever the exponential growth or decay is. So now I'm going to be able to say I have 380 insects to be equal to 130, well, yeah, over E times 3K to be multiplied by e to the 7k power. Well, the properties of exponents, the 3 in the denominator and the 7 in the numerator, we can subtract those numbers from each other, and that will simplify to be 380 to be equal to 130 times e to the 4k power. And now that I've done that, we can find the constant of proportionality. We can actually find k now. So let's finish working this through to find k. So 380 divided by 130 will simplify as a fraction to be 38 over 13 to be equal to e to the 4k power. And again, we've seen this a few times already. To get the k out of the exponent spot, we have to convert the exponent to a logarithm. So I will get the natural log of 38 over 13 to be equal to 4k. Now you divide both sides by 4, and this one will be approximately 0.286 to be approximately equal to k. And again, we want to take that number, save that number in your calculator. Okay. Well, now we can actually go back and answer the question. The question initially was asking us how many insects were initially present, meaning that we had to find C. That would be the number of insects that are initially present. Well, through a little bit of creative thinking and some arithmetic here, we were able to come up with an expression that was equivalent to C, even though it didn't give us the number for C. And that allowed us to find the constant of proportionality, K. And now I can actually go back and solve for C. Now, which equation do I use to solve for C? Well, to solve for C, and let me do that in a different color. Let's try purple. I can use either of these two equations to solve for C. It really doesn't make a difference which one you use. I'm going to use the first one simply because the numbers are smaller. So we already know that, and partly because I already have this expression here, we know that C is going to be equal to 130 divided by 3, I'm sorry, not 3, E to the 3k power, and in this case, the k power was, or the k number was about 0.286, and time in this case was 3. So you can just type that directly into your calculator. Remember, you saved the 0.286 number. So this would be our final approximated number of 58.15 insects initially present. So we'd probably really have to round it up to be about 59, but that is how many insects initially were present at the beginning of the experiment. So the last examples that we're going to be looking at here are going to hopefully take us back to a little bit of chemistry recall, because this is typically where you as a sophomore or whenever you take chemistry, this is probably where you would have seen half-life questions when you're talking about radioactive decay of certain elements. And this is essentially the same thing that we're going to be looking at here. We want to be able to find the half-life of something. And the equation that we're working with is still going to be the same. This that we have here is the same equation that we've been working with, where we said it was y is equal to c times e to the kt power, except now here, where they were saying c, they have a with a subscript of 0, where we would say that is a naught. That is still the initial, that's still the initial amount, whatever you start with in your problem. So let's take a look at the example and see what we know and what we need to figure out. A zircon sample contains 4,000 atoms of the radioactive element 235U, and I don't know what that is exactly. I'm not a chemistry teacher. Maybe that's uranium 235. I hope not, if it's in zircon, because we wear that on our fingers and ears a lot. Given that 235U has a half-life of 700 million years, that's a very long time, how long would it take to decay to 125 atoms? Well, let's see. What do we know so far? We know we have, at some point in time that we don't know yet, we are going to have 125 atoms. We also know that the initial amount present, A naught, or A sub 0, is equal to 4,000 atoms. And we also know that the half-life, T, is going to be 700 million years. And what we're trying to do is we're trying to find out time. We want to be able to solve for time that will give us 125,000. Now, if you notice in the equation, one thing that we absolutely do not know right now is what is k going to be. We don't know that right now. The constant of proportionality has not been given to us. So we have to figure that out first. Now, half-life is real convenient in the fact that we know that we start with a certain amount. So after 700 million years, we're going to have half of that amount. So after 700 million years, we're going to have 2,000 atoms. And this really isn't necessary if you understand half-life to begin with. We're going to say 2,000. That's half of what we started with initially of 4,000 times e to the k power, or let's actually put that the other way around, because we know, and I'm not going to write 700 million, I'm going to just write 700 for millions of years. So 700k, okay? And so when we divide to begin with, we start with 1/2 is equal to e to the 700k power. And at this point, again, I really don't think we should be super surprised what's going to happen. We have to get k out of the exponent spot, so we will use our log loop with properties of logarithms to change the exponent to a logarithm. So that will give me the natural log of 1/2 is equal to 700k. So when you take the natural log of 1/2 and you divide it by 700, that will give you about negative 0.0, and I'm going to do more than 3 decimals for this one because it's a very small number. 0.000990 is approximately equal to the constant of proportionality. And again, take that number and save it in your calculator. Well, now that we have the value of k, the constant of proportionality, we can actually solve the equation. We can solve for time, the amount of time it will take us to get to 125 atoms left. And I don't think I changed, okay, I did change my color. So now let's solve for time. Well, we know at whatever the time is that we have to figure out, we have 125 atoms of the element left. We still started with 400, or I'm sorry, not 400, 4,000 atoms of that element. And in this case, we have e to the kt power, which in this case, we'll say, this one's not going to be a very nice number. We'll say negative 0.000990 times time. And now we're going to solve. And I think if once we have the equation written, I don't think it's really going to be all that difficult to work out. Divide by 4,000. 125 divided by 4,000 will give me 1 over 32 to be equal to e to the negative 0.000990t. And again, t is in the exponent's position, so we have to take the log loop here, and I will get the natural log of 1 over 32 to be equal to negative 0.000990 times time. And you divide by, you have that number saved in your calculator, and you divide that into the natural log of 1 over 32, and you're going to get the astonishing number of 3,500 million years for time. Quite a long time. So that is essentially what we're going to be doing with a lot of half-life problems. So here is our last one, and it's not strictly a half-life question. It's just giving you a differential equation to start with, and it's simply going to ask you a question about it. We have a cup of hot chocolate placed on a table that cools at a rate of d of c, or the derivative of c with respect to time. So c is probably going to be Celsius. But again, they're just simply saying where C represents the temperature of the hot topic. Okay, no, we are doing it in degrees Fahrenheit. A little confusing to say C if you're not talking about Celsius, but anyway, this is, and just as a side note, this is very much going to relate to things that you may have seen with Newton's law of cooling if you did this stuff with in pre-calculus. There is a section in BC calculus for Newton's law of cooling that some of you may or may encounter in your studies, but how much time, or I'm sorry, after 10 minutes, the coffee of being 160 degrees initially, what was the temperature 10 minutes later? So we're going to have to kind of work this one from start to finish. So going way back to the beginning of the lesson where we had a differential, oh, I'm sorry, not a differential, but a separable differential equation, and we had to convert it into kind of a standard equation where we had to separate the variables and then take the integral of both sides. We're going to do the exact same thing here. So starting off with, let me go ahead and just write the equation down so I don't throw anybody off. We have d, oh, hello, that was unexpected. Let me give myself a little more space now. So fingers crossed, no more computer glitches. D, turn the pen back on. D of C, or the derivative of C with respect to time, dt, is equal to negative 0.05 times C minus 75. And we don't really need to write the degrees Fahrenheit. We just kind of go with that. Well, we want to be able to separate the variables, so we're going to divide by the expression in parentheses and multiply by the dt in the denominator, and that is going to give you dc divided by c minus 75 to be equal to negative 0.05 times dt. And just like what we did in the first example where we proved that equation that you've probably already been using in previous math classes, this is where we're going to take the integral of both sides. Let's see what happens from here. Let me give myself a little bit more space. Let's come down some. So when I take the integral of both sides, the integral of the left side, because we have that fraction in the denominator, you could also look at the left side of the equation as 1 over c minus 75 times dc, if that helps. But essentially what we're going to be doing is we're going to take the antiderivative of the fraction 1 over c minus 75. And when I take the antiderivative of that fraction, I'm going to get the, oh, why isn't my pen turned back on? The natural log of c minus 75. And when I take the derivative of the right side, remember that negative 0.05, that's a constant. You could pull it out of the integral. We're not actually taking the antiderivative of the 0.05 number. We're only taking the antiderivative of the dt. So I'm going to get negative 0.05. So the antiderivative of dt will give me 1t and a constant for our indefinite integral. Well, in order to be able to work the problem out, we do need to, find what is the specific value of c in this case. And so let's go ahead and work through what we have. At this point, because we have a c in two different places, we definitely want to try to get it out of the logarithm. And the only way that we can do that is by, you guessed it, taking a log loop. So that'll give me e to the negative 0.05t plus c power is equal to c minus 75. Okay, so going back again to the original example, we can take the stuff on the left and separate it with properties of exponents into e to the negative 0.05 t power times e to the c power to be equal to c minus 75. And again, this thing right here, this is just a constant. That is just going to be a constant that we represent as the number c, or not, the letter c. So I have c times e to the negative 0.05 t power to be equal to c minus 75. Okay, so now where do we go from here? Well, the question initially says, what will the temperature be, or I'm sorry, what will the temperature be in 10 minutes? So we have to be able to solve this for the temperature. And that is going to take us from here. We're going to take the 75 on the right side of the equal sign. And I'm going to just kind of come up here some because I don't want to keep going down. And I can't write an arrow. Write an arrow. Okay, so take the 75 on the right side and move it over to the left side. And what we're going to wind up with is we will have 75. 75 is equal. Okay, let me just start that bit over. 75 plus c times e to the negative 0.05 t power will be equal to, and in this case what we're looking for, c of t. So the c that remains on the right side of the equal sign, that becomes our function notation, and that is how we're going to now be able to identify what the temperature will be after 10 minutes. Okay, so now we can say, let me just go ahead and reverse that. So I'm going to say C of 10 will be equal to 75 plus, oh, what am I missing here? Oh, I don't know don't have a value of C yet. Well, that's pretty easy to get. What is C going to be? Let me back up just a teeny bit here. we need to know what was this initial amount. Well, we know the initial amount of the temperature was 160 degrees. And the question is asking us, what will the temperature be 10 minutes later? So how are we going to use that information? Well, we know that we had at some point C minus 75, so 160 minus 7. Oh, hello. 160 minus, come on. It's late and my computer's not wanting to cooperate here. Negative. So we had here C minus 175. At some point we had 160 minus the 75 degrees, and so that will give us a C value here of 85 degrees. There we go. So now I have 75, oh wait, we'll just keep going, plus 85 times e to the negative 0.05 times 10 for 10 minutes is equal to C of 10. And now we can just type everything that we see on the left side into the calculator, and that will give us about 126.555 degrees Fahrenheit to be approximately equal to C of 10. Okay, so I kind of flubbed up a little bit on this last bit here to find that value here of C, and I apologize for that, but other than that, I'm feeling very confident in our answer here. And that is the long and short of, hopefully you saw enough examples or got enough out of the examples and the way I explain them to get you through whatever lessons that you're going to be working on. So we're going to go ahead and wrap it up here. Thanks for watching and take care.